Good morning, guys. Welcome back. Can we start with some green check marks, please, and then we'll get going. If you ran into any issues with the acceleration questions from last day, or sorry, not the acceleration, the graphing velocity stuff from the end of Unit 8 there, 8, 1, 2, or 3, if you could throw those questions into chat, I can go through anything you had issues with. If not, Unit 8 should be kind of done and submitted, and a few of you guys have submitted it already and have written the test, so that's great. There's only 2 sections in Unit 9, so we're nearly done, and it's on acceleration, so it should go fairly quickly. I envision today and Tuesday, maybe like half the class on Tuesday, and then we'll be finished. So I don't see any questions from Unit 8. So that might be a good thing, might be a bad thing. I'm just going to continue on with Unit 9, and as it turns out, Unit 9 looks almost the exact same as Unit 8, except instead of just talking about velocity and distance, now we're going to talk about acceleration and what that means. So let's get started. So when we talk about uniform motion, and we did at the end of the last unit, we're talking about objects that are traveling the same distance in equal time intervals. So it's just kind of a really complex, convoluted way of saying something that's traveling at a very constant rate. It's not speeding up, it's not slowing down. So in the diagram here, you can see that, find my cursor, there it is, that at 0 meters, you're at times 0. 2 seconds later, you're at 4 meters. 2 seconds later, you're at 8 meters. 2 seconds later, you're at 12 meters. So each 2-second interval, you've traveled 4 meters. And that is kind of a fancy way of saying it's going just at a very constant speed. If you could imagine either the time changing or the distance changing, let's say it took 2 seconds to get to 4 meters, and then it took only 1 second to get to 8 meters. Well, that wouldn't be uniform. You'd be traveling the same distance, 4 meters, but in half the time. So you'd have to speed up in order to do that. Or if you could imagine the 4 meters in 2 seconds, and then another 2 seconds later, this was a number like 10 meters. Well, in the first 2 seconds, you went 4 meters. In the second 2 seconds, you would have gone 6 meters. So that would be something that was speeding up. So you can speed up and slow down, and that's what we're going to talk about today, acceleration. So here's an example, really similar situation, a car, and it is not uniform motion. You can see that you have different time intervals, so 2 seconds per time interval, and in each time interval you're going a different distance. So in this time interval you went 6 meters. In this time interval, which was the same amount of time, 2 seconds, you only went 2 meters. And then in this time interval, you went from 2 to 8, so that was 6 meters. In this time interval, you went 2 meters, so you went 2, and then 6, and then 2, and then 6. So you're speeding up and slowing down. That's non-uniform motion. It's motion where your velocity or speed is being changed. So we can come up with a way to describe that, in words, and we can come up with a way to describe it mathematically, and we call it a change in velocity. It means you are not engaging in uniform motion. You're either speeding up or slowing down, and we can calculate what the change is. So if you're going really fast and then you slow down, you changed your speed. If you're going really slow and you sped up, you've changed your speed. And that's what this delta V is. So remember the triangle's Greek letter, it's delta, and it means change. The little arrows above the V and the V and the V, those just indicate that we're talking about a vector as opposed to just speed or a scalar. So you can, I don't want to say ignore them, they are there, they are somewhat important, but if you kind of forget what they mean, it's not really going to have a huge effect on anything you do. So we can run into 3 situations. The change in velocity can be positive if your final is bigger than your initial. The change in velocity can be negative, meaning your initial is bigger than your final. And then your change in velocity can be 0, which means you're traveling with uniform motion. And we have these little subscripts, the F and the I here, to indicate the final velocity and the initial velocity. So most of the questions from here on out are actually going to have two different velocities in them. So F is going to represent final, I is going to represent initial. So you have your initial velocity, that's how fast you're going at the start, and then you have your final velocity is how fast you're going at the end. All right. We have two different images here where velocity is changing. How would we describe them? So like a car speeding up. Is its initial velocity bigger than its final? Is it final bigger than its initial? What about a space shuttle landing? Geez, this picture is going to be like a thing of the past here soon. There's going to be, nobody remembers what space shuttles are anymore. What's happening to the space shuttle? So let's maybe talk about the space shuttle here for a second. So the space shuttle is coming into Earth's atmosphere. It's going to be going really fast. And then what happens when the space shuttle is done? What is the space shuttle's final velocity going to be? So Kyla, yeah, it's definitely slowing down. But what's the final velocity of a space shuttle going to be? If we were talking about VF. It is 0, yeah. So when we talk about the final velocity of an object that's slowing down, it's going to come to a stop. You can imagine some poor astronauts trying to bail out of a space shuttle that's kind of cruising along the runway. If it didn't stop, it would make watching the space shuttle landings even more exciting. Whereas something like a race car has kind of an opposite scenario. A race car starts at the starting line, and it's going to be at a complete stop to begin with, and then the light's going to go green, and then it's going to take off, and it's going to speed up until it reaches its maximum velocity at the end of the racetrack. So you have kind of opposite situations. The race car is starting at 0 and finishing at a very high rate of speed, whereas the space shuttle is coming at a very high rate of speed, and it's actually going to have a final velocity of 0. So let's look at a few examples here and see if we can wrap our heads around this change of velocity stuff. So let's just skip example number 1 because we'll actually talk about it next day when we deal with graphing this sort of stuff. So let's just start with example number 2. An object moving in the positive direction is positively accelerating the distance traveled each second would be. So if you have some sort of object, like a car or a ball, I'm really good at drawing cars, so I always use cars. It's traveling in the positive direction, so we'll call that positive. And it's accelerating, so it's increasing its velocity. Josh, you're on like grade 11 physics there. We don't have to worry about distance, acceleration formula like that. The distance traveled each second would it be the same, or would it be changing? What do we think? We're just very basic to start out here, Josh, although if you take grade 11 physics, you'll definitely use that formula a lot. Yeah, increasing for sure. So, if it's speeding up, let's give it some distance here of, like 2 meters, and let's say that took, 2 seconds to complete. And then we have another 2 meters, so we're at 4 meters. If it's speeding up, it's not going to take 2 seconds. Maybe it takes 1.5 seconds to get that next 2 meters, and then you have up to 6 meters, and maybe that only takes 1 second now. So the distance traveled in each second would be increasing because the faster you're going, the larger the distance you're going to travel. All right, so let's say we have a car that's traveling along at a steady 100 kilometers per hour. You're on the highway, cruising along. Is it accelerating? Is it velocity changing? What do we think? Is that constant velocity? Is it increasing its velocity? Is it decreasing its velocity? Oh, that's a good point. yeah, so if you run into, a stop sign, stoplight, I hope there's no stop signs on roads that have a 100 km/h speed limit. It's not accelerating, no. So the questions that come up in this unit are going to be quite literal. There's going to be sort of no interpretation to them, like stoplights or slow people. So if it says it's driving along at 100 km/h, that would be a constant velocity. Or we could call it uniform motion. And we'd have no acceleration. Example number 4 is kind of a good sort of, in physics or science, you can call them like thought experiments. I think Einstein had a fancy German word for them. They were like Gedankens or something like that. Does anyone speak German? Gedanken, does that make sense? I don't know why I remember that. So imagine if you've ever been on an airplane. If you fell asleep, you had a blindfold on, and let's say you're like really asleep, you could have landed, maybe you're still in the air. Would you know the difference between, aside from the noise, would you know the difference between being on the ground and being in the air? Or if you've never been on a plane before, you could have a very similar experience on like a car or a bus. If you were inside a bus and the windows were blacked out, so you couldn't see anything outside, would you know if you were moving or not? What do you think? Yes. How would you know, Kyla? You can feel it. Okay, so what do you mean you can feel it? Inertia after stopping. We're not stopping. We're traveling, can't see outside. We don't know if we're stopped or we don't know if we're moving. The g-force. Okay, so let's expand on the g-force idea a little bit. What does g-force mean? Jonah Bumpy for sure would be one of the giveaways. Does anybody know what g-force means? Like everybody just throws around, you feel some acceleration in g-force. What does the G mean? Why have we used the letter G? The force of gravity, for sure, gravity, yeah. So everyone's kind of decided on gravity. So it turns out that objects that are, falling towards Earth, if I drop my pen, it's going to fall. It's going to experience some acceleration towards the ground, and it'll eventually hit the ground. So that is what we call the acceleration due to gravity. And when we talk about g-forces in like planes and cars and things like that, we always just talk about how many g's you would experience. If you were an astronaut, you're launching in a spaceship going into orbit up to the space station, you're going to experience some g-force. And basically what that means is as the rocket is accelerating upwards, is increasing its velocity, you kind of get pushed back into your seat and it kind of feels like you're standing on Earth. So in a spaceship, you're going to experience like 3-4 times the force you would feel on Earth. So if you're sitting in your space shuttle, you're going to feel about 4 times heavier than you were if you're just standing on Earth. So that's what we mean by g-force. And that's what we're talking about in this question. So let's just imagine this for a second. Let's imagine a completely perfect scenario. So we don't have any bumps, no turbulence. You can think of another situation that we use a lot in physics are elevators, because you can't see out of an elevator generally. It's in the middle of a building. When you're going between floors, you're not starting, you're not stopped, but in between floors, can you tell if you're moving or stopped? Same in a car. If you could imagine a car on a perfectly smooth road, no bumps at all, the car wasn't speeding up or slowing down, windows were completely blacked out, would you be able to tell if you're moving or not? Same on a plane. Plane's a little bit easier example because generally you're not going to experience any bumps if things are going well. So Jonah, what would indicate to you that you were moving if you were in a car that was completely blacked out, you couldn't tell if the road was, bumpy, it was completely smooth road, how would you know you were moving? And that can extend to everyone, not just Jonah necessarily. You just know, I feel like. Has anybody ever been on a plane, like a long plane? Yeah, so when you're in a long plane ride, whatever, it doesn't necessarily need to be. The reason I use long is because if you fly to like Vancouver, you're climbing, and then you get there and you're like in Vancouver. So there's not a real place where you've kind of reached altitude and you're cruising. If you've ever been on an airplane, you get up, maybe you gotta go pee, you kind of walk down the aisle to the bathroom. Is there anything in terms of your movement, out of the seat and back to the bathroom that would indicate that you were flying at, 500 kilometers an hour in a perfect plane, no turbulence? It's kind of unsteady because the plane bumps around. And imagine if the plane weren't experiencing turbulence. It was completely perfect skies. Would you know you were traveling at 600 kilometers an hour, 500 kilometers an hour? Madison, probably not. All right, we're getting there. So gravity is slightly increased. Why would the gravity be increased? It's actually decreased the higher you get off the surface of the Earth. You go to the top of Mount Everest, slightly less gravity, but not enough for you to notice the difference. Okay, we're getting somewhere now. So let's go back to the car scenario. Let's pretend we're not a car. Let's pretend we're on a train now. And not like a regular train. You guys have probably never been on trains before, so this may be a terrible example, but use our imagination. Have you been on like any cool train rides? I've been on a few trains before, but there's not a lot of trains in Canada. Lots of mountains and things. Oh, to Venice, yeah, fancy Italy trains. All right, so imagine we're on a train. We're not on like a train with train wheels. We're on one of them fancy like Japanese maglev trains. So there's actually nothing touching the tracks. It's floating, literally floating, and it's cruising along. And those trains can go about 200 kilometers an hour. They're very fast. Some of them even faster. Would you know, if you couldn't see outside, that you were traveling 200 kilometers per hour? And how would that feel in comparison to maybe being on an airplane traveling 500 kilometers per hour, or being in a car traveling 50 kilometers per hour? So all of the things you guys have all been on trains, 2 of you? That's not bad. I take back my statement that you guys probably haven't been on trains. Many of you have experienced trains, which is just terrific. Kind of glitching out here in my little picture. That's kind of fun. Frame rate's kind of a little slow. Subways in New York. Subways are another example of a train. All right, everybody's been on a train. I'm just going to use trains for examples for the rest of the questions. We're gonna cut me out. Can you guys hear my audio still? Is it just the picture that's slow? Yeah, is the picture slow on your end? Kind of like really glitching out? A little, yeah? All right. I feel like there's a glitch in the matrix. All right, so I'm going to get back to this. I've kind of beat this question to death, but the reality is that if you are on an object that's traveling at uniform motion, and I think maybe an elevator is a good example, or a train, if you're traveling in uniform motion, you're not speeding up or not slowing down, there would be no reason to indicate to you with your senses that you were moving. And for those of you who experience motion sickness, and I think Kyla said you did, the reason you experience motion sickness is because your eyes are experiencing something different than your inner ear in terms of movement and things. So if you were completely blindfolded, you had your ears plugged, and you couldn't see outside, you wouldn't know you were moving. And that's the case inside of an airplane for sure, because you're traveling extremely fast, but there's nothing to indicate that you're traveling so fast. But if you, on an airplane or in a car, if you speed up, then you kind of get pushed back into your seat. Or if somebody slams on the brakes, you get thrown forward. that's acceleration. That is what you feel as acceleration. That's a change in velocity. If you speed up, you get pushed back into your seat. And there's videos on YouTube that, I'm kind of a car guy, they pick really, really fast cars and they'll take a $100 bill and they'll stick it to the dash. And they'll say, I'm going to just accelerate here. If you can grab that $100 bill, you can keep it. And the cars accelerate so fast, they are going so fast that you physically can't reach the $100 bill on the dash to grab it just because there's so much acceleration. Similar sorts of things in a car. If you've ever traveled and the light turns red and it's kind of like a panic stop, or there's someone stopped in front of you or an object on the road, you slam on the brakes, you go flying forward. That's acceleration. So back to example number 4. You couldn't tell if you were moving only if the plane either sped up, slowed down, or even if it changed elevation. So if you have been on a plane before, a car even, when the plane takes off, you get pushed back into your seat. It's accelerating. If you're in a car, you're at a stoplight, you're completely stopped, you just kind of sit there, everything feels normal, and then you take off, you kind of get pushed back into your seat, and then you get to the next stoplight, you slow down. When you're traveling at the speed limit, you don't feel any different than you normally would, but as soon as you hit the brakes, now you get, feel like you're moving forward. So hopefully we kind of understand that. Everybody's experienced this before, but it's kind of hard to kind of wrap your brain around it. Next time you're in a car, you're driving, to the grocery store or whatever with your parents, or driving, because a lot of you drive now. Think about it. When you're traveling the speed limit, you're going at a completely constant speed. There's nothing in your car that would indicate that you are moving. If you couldn't see outside, you wouldn't know that you were moving. And I guess the best example of that is a train. Always trains. Everybody's been on a train. So that feeling when you kind of get pushed into the seat, or you get thrown forward, or even when a car turns, you kind of get pushed to the outside of the car as the car turns, that's acceleration. That's what we call acceleration. And it's always dependent on a change in velocity. In Science 10, we only talk about one dimension, so going forward or backwards or up and down or left or right. But in a car, if you turn a corner, you're changing your velocity. Remember, velocity has a direction. You're not going forward anymore, now you're going that way. As you turn, you get thrown to the outside of the car, and that's an acceleration as well. Objects with the same change of velocity can have different accelerations, which is kind of a weird idea. So let's imagine these two cars here, and the example is kind of written out here. They're both going to go from 0 kilometers per hour, so at a start line, and they're both going to go to 60 kilometers per hour. So chances are the drag racing car is going to be able to get there a lot faster to that 60 kilometer per hour mark than the old car there. So they're both going to change their velocity from 0 to 60. But because the drag racing car can do it so much faster, it's going to have a greater acceleration. And if you can imagine being in these two examples, the drag race car is going to push you right back into your seat. You're going to have a tough time holding on, while as the other car, you're not really going to feel much because it's just going to accelerate so slowly. So the faster you change your velocity, the greater the acceleration. Same if you're driving your car, doing the speed limit, and there's like a squirrel on the road. So you hit the brakes and you change your velocity very quick. You're going 50, now you're going 0. The faster that happens, the smaller the amount of time, the larger the acceleration. All right. So the relationship of acceleration, change of velocity, and time is given by this formula. Acceleration is a change in velocity divided by a change in time. And this formula is given on your data booklet on the last page. In the last two columns, you have the acceleration formulas and the change of velocity formulas. So let's look at an example here where we have a pool ball. You hit the pool ball, it hits the bumper on the end, and it bounces back, traveling the opposite direction. So let's say you initially hit it at 2.5 meters per second, it hits the wall, and it bounces off the wall at 1.5 meters per second. So it slows down a little bit while it changed its velocity in hitting the wall there. And let's say that the ball was touching the cushion for 0.2 seconds. That's what's going to cause the ball to change its velocity, is it actually physically bumping into that end barrier. So we need to calculate the acceleration of the pool ball. It's changing its velocity. It was initially going 2.5, now it's going 1.5 the opposite direction. There's a clear change in velocity there. We want to figure out, how fast it took it to change that velocity, and then we can actually calculate something called the acceleration of the ball. So maybe not the best example to start with, but we'll do it anyways. There's one kind of important piece of information here, and written in brackets at the end. It says, assume towards the cushion is the positive direction. So everything going towards the cushion is positive. So if we talk about this guy here, everything going this way is positive. That means everything going the other way, so I didn't want that, everything going the other way is going to be negative. So initially we have a positive velocity, 2.5, and then we're going to finish with a negative velocity, negative 1.5. So the question asks us to find the acceleration. What other pieces of information do we have? We have a pool ball is traveling at 2.5 meters per second. So I'm going to call that v with a little I next to it, because that's our initial velocity. We're also told that it bounces off at 1.5 meters per second. So that's going to be your final velocity. And we also know that the ball was in contact with the wall for 0.2 seconds, which is going to indicate the time, or change in time. Okay. There's two ways to do these questions. You can do them in 2 steps, or you can do them in 1, and maybe I'll show both ways. The first way I'm going to do is going to find us the change in velocity, because we need to know how much the velocity changed in order to calculate the acceleration. So a change in velocity, and this is just right off your formula sheet, is going to be the final velocity minus the initial velocity. If we take where we ended in terms of velocity and we subtract what we started with, we should get our change in velocity. All right, so our final velocity was 1.5 meters per second, and that final velocity is going to be negative because it was going to the left. And remember, all the negative indicates is that we have a different direction. Then we're going to subtract the initial velocity, and we indicated that the initial velocity, the velocity that the ball started with, was 2.5 meters per second. Now, that's going to be positive because everything to the right is going to have a positive velocity. All right, so our change in velocity is going to be the final minus the initial. So negative 1.5 minus 2.5. So that should give us negative 4 meters per second. So the velocity changed by negative 4 meters per second. All right, so we have this acceleration which we're trying to find. Our change in velocity is now negative 4 meters per second. And we're going to divide that by our time, which was 0.2 seconds. So 4 divided by 2 is going to give me 2, but it's 4 divided by 0.2, so it's going to give me 20. Negative 20 meters per second. And this is the units for acceleration, meters per second squared, because we have meters per second divided by seconds. So it's like meters per second per second. And And if we kind of think about meters per second, kind of makes sense because we've talked about the acceleration as being the amount you're changing your velocity for some period of time. So if you had a really big change of velocity in a really large amount of time, that's how many meters per second you changed per second. So if you change your meters per second a lot per second, then you have a big acceleration. If that makes any sense at all. So there you go. That's maybe a bit of a more difficult one to start with. Typically, they're going to be a lot more straightforward. So the relationship of change of velocity, acceleration, and time is given the formula. Obviously, there's three different ways to write the formula. We can have acceleration as change of velocity over time. We can have velocity is acceleration times time. And then we can have time, which is acceleration. Get this right. We'll do it in the next example. So we could be given some different information. We could be asked to calculate the change of velocity given the acceleration and amount of time. So that's what this question's asking. So maybe let's just look at this. A car accelerates from rest at 3.2 or 3.0 meters per second squared. That should read like this, 3.0 meters per second squared. And that is going to be our acceleration. So it's giving us an acceleration. We're also given a time. And the question's asking us, what is the velocity of the car? There's one other piece of information in the question here that if you don't really look for it, you probably wouldn't see it. And in a lot of questions, it's going to be a really, really important piece of information. And this question, it won't make a huge difference, but does anybody see the one other thing that I missed? It's not a number, but it actually indicates a number to us. The end velocity, we know that it goes, I guess it's kind of what is the velocity of the car at the end. So velocity of the car at 5. Forward's there, yeah, we know everything's forward. There's one other thing. What does this mean from rest? I only bring it to your attention because it happens a lot in physics questions. You'll see objects accelerating for rest. What's significant about that? That's from 0 for sure. So when you say from 0, what you actually mean is that your initial velocity, vi, is going to be 0. Now, in this question, it's not going to make a whole lot of a difference, but it will come up time and time again, and in some questions, it'll be important. So what's the velocity of the car at the end of the 5 seconds? So we want to find the velocity. We've got our formula here, and I'm just going to go, instead of delta v with the line, I'm just going to go velocity is acceleration times time. Just to kind of simplify things. Essentially, this formula and this are the same thing, but they just have a lot of fancy other stuff in there that kind of scares grade 10 students. So if it's kind of scaring you, that's okay. Just go velocity is acceleration times time. So velocity is acceleration. What's the acceleration? The acceleration is 3.0 meters per second. I guess I could do that like this. 3.0 meters per second squared was the acceleration, and then the time that took was 5.0 seconds. So our velocity is going to be 3 times 5. 3 times 5 is 15, and we get meters per second is our velocity. One thing that I will point out that the physics teacher in me wants to show, if we just kind of ignore the question for a second and just look at the units. We have meters per second here, and we're going to multiply that by seconds, or seconds over 1 from here. How do the units work out? We'll have meters over seconds squared, and then I have seconds on the top. So if this was a grade 10 math question, I'd say, okay, m over s squared times s. And you'd say, okay, I got this. I have one s on the top, I have 2 on the bottom, so I'd get rid of that, I would change it to a 1. And my units would end up being meters over seconds. And that's what we end up with, because we know that a velocity has units of meters per second. So is that the answer? Is that it? Are we done? Well, I guess we're pretty close. It's asked for the velocity of the car at the end of 5 seconds. So if we started from rest and we went to 15, that would be the velocity at 5 seconds. And the only thing, as Eric mentioned before, is that we should probably indicate a direction. And in this example, everything's moving forward. So everything should be going forward. So that's going to be a little bit more like the types of questions you're going to see in this section. Just pretty straightforward, simple 3-variable type questions. You just kind of have to sift through the question to find the important information. Pardon me. All right, acceleration is a vector. Its official definition is the rate of change of velocity. And I was mentioning this earlier. If we talked about changing your velocity, so you change your velocity by 10 meters per second every second. That would be an acceleration. How long did it take you to change your velocity by 10? To go from 0 to 10 or 10 to 20? Well, each change in velocity took you 1 second. So that's an acceleration, or 10 meters per second squared. So a truck started from rest. Again, this is an important piece of information. Started from rest. That means our initial velocity is going to be 0. And maintained 10 meters per second squared acceleration. If you get nothing else out of this whole unit other than you're able to recognize the difference between an acceleration and a velocity, that would make me happy. Because a lot of times students get to the end of the course and they're like, I've just done so much work and I'm so confused. And units are going to help you a lot in these types of questions. So if you can recognize that 10 meters per second squared is not the same as 10 meters per second. Those are different things. This is a velocity. This is an acceleration. If you can recognize the difference between acceleration and velocity, you probably will do just fine in Unit 9. All right, so we have acceleration 10 meters per second squared. So that's our acceleration. We have that acceleration for 5 seconds. So that is a time. And it said how fast would it be going after each second. All right, it's a truck, so I'm going to draw a truck. Here we go. I'm going to draw a dump truck. That is a good-looking truck. I know you guys were all thinking it. Nobody wanted to write it in the chat. Pretty proud of that truck. All right, so the truck, it started from rest. So we have time 0, and our velocity is 0 meters per second. So it's not going anywhere. It's at rest. It says it accelerated at 10 meters per second squared for 5 seconds. And then it asks us how fast would it be going after each second. So let's put a little marker out here. There's 1 second. Another marker, 2 seconds. Another marker, 3 seconds. 4 seconds. I'm gonna run out of room. Nope. 5 seconds. There we go. So instead of using a formula, which we could use, Josh, for sure we could use a formula, it's asking how fast it's going after each second. So instead of using the formula 5 times, we can just kind of maybe think about it. So the truck goes from here to here. There's no chance I'm going to be able to redraw that truck, so I'm just going to draw a little arrow there. All right, so after 1 second, how fast is the truck going at that first second mark? What's its velocity going to be here? Josh is going with 2. What page are we supposed to be on? I'm not sure. Balls being thrown, acceleration. Yeah, this doesn't match up with your notes. So maybe just be jotting this down. Graphing, yeah. So this is just for your benefit. All right, so it says that the car is accelerating, truck is accelerating at 10 meters per second squared. Or we can think of this as 10 meters per second. So after 1 second, how fast would we be going? Josh, I only re-asked the question because 2 is not going to be right. But if you think about 10 meters per second, each second, what would you guess if you had a second guess, perhaps? 10 meters per second. You would, in fact, be going 10 meters per second after 1 second. How fast would you be going after your next second if you change your velocity by 10 meters per second every second? So if you went from 0 to 10 after 1 second, yeah, that would be correct, Josh. It is maintaining its acceleration. Maybe when we get to the end here, you might make more sense. So after 2 seconds, you'd be going 20 meters per second. After 3 seconds, you would be going 30 meters per second. After 4 seconds, you'd be going 40 meters per second. And after 5 seconds, you'd be going 50 meters per second. So each second, you're increasing your velocity by 10 meters per second. We could use a formula to calculate the velocity at each interval. Or at the end of the 5 seconds, and that would look like velocity is acceleration times time. Yes, AT is VF, velocity, acceleration times time. AT is VF, velocity is acceleration times time. Your A and your T shouldn't be together there, Josh, because if you have, I'll just write up top, if you have acceleration as velocity divided by time, I guess you could, yes. So velocity is acceleration times time, and then we'd have final velocity minus initial velocity is acceleration times time, and our initial velocity, initial I, is going to be 0. So that would work. Yes, you could do it at each time interval. So 1 times 10 is 10, 2 times 10 is 20, 3 times 10 is 30, 4 times 10 is 40. That would work. That would make sense. All right, there are 3 examples here. Let's give you guys a chance to do them. So we have acceleration is velocity divided by time. We have velocity is acceleration times time. And we have time is velocity divided by the acceleration. Those are the 3 formulas that you're going to encounter. Have a go at these 3. So the truck starting from rest, we have an acceleration. It says accelerates uniformly. And then 18 meters per second. Because this is not seconds squared, if you were just looking at units, this is actually a final velocity here. And then we have a time here at 4.5, and then it asks for the acceleration. So what is the acceleration? Toboggan moving 5 decelerates backwards at negative 4 meters per second squared. Again, this should be negative 4 meters per second squared. And then again, we have a time of 10 seconds. What's the toboggan's velocity at the end? So it's asking for final velocity. And then how much time? So we're trying to find the time. So we're traveling at 12, we're changing to 26. So your initial velocity, you have a final velocity, and then you have an acceleration. All right, so I'll give you 5 minutes to go through those 3 questions and just see what you can do. See if you can find the right formula, see if you can plug the numbers in, and then we'll go through the answers together in about 5 or so minutes. Good luck. All right, guys, did anyone feeling brave? Anyone want to put in an answer for example number 2, the truck uniformly to 18, what's the truck's acceleration? Did anyone find an acceleration there? Maybe if one brave person puts their answer in, the second brave person will agree with them and confirm everything. 4, all right. We have an answer of 4 meters per second squared. Did anybody agree with Eric? Disagree? I mean, Eric's a pretty smart guy. If you got 4, it's probably 4. Anyone want to challenge Eric? All right, so let's see what we can do here. We're trying to find the acceleration. So I know from my formula up here that acceleration is going to be the velocity divided by how long it took to change that velocity. So acceleration is velocity divided by time. It says it accelerates uniformly to 18. So we're going to end up at 18 meters per second is going to be our velocity. And it took 4.5 seconds to get there. 18 divided by 4.5, I have a calculator. So 18 divided by 4.5 is going to be 4. Brilliant. So we'll go 4 meters per second squared. And then I know it doesn't really indicate any sort of direction or anything there, but it's just a really good habit to write in a word like forward. And even if you don't know the direction, just make it up. Because it's asking for an acceleration should have a direction associated with it. All right, example numero 3, numero 3. Toboggan moving 5, has a negative acceleration, so it's slowing down. And it takes 10 seconds for it to slow down. And what's the final velocity going to be? Anyone feeling brave there? That's a little bit more of a difficult question, but I think you guys could probably handle it. Does the provincial count for marks, or is it for the government, or whatever? No provincial exam. So no, it doesn't count for marks, and the government doesn't care anymore. You guys will have a final exam, which will be on the second half of the course, and that will indeed count for marks towards your final grade. No provincials anymore, though. They're done. You guys will have some sort of science math assessment next year maybe or something. I don't know. I don't even know if the government knows what it is going to look like, which will not count for marks, but that's not this year. That's in the future. You'll encounter it eventually. Yeah, Kyla, if you fail a class, you must redo it. So you guys are in grade 10 now, so that's what we like to call the graduation program. Basically, you have 3 years, starting from when you start grade 10, to pass the required courses and get enough credits to graduate. If you fail a course, you do need to redo it. Whereas in middle school, when you're in like grade 8, you did really good in everything, except you did really, really bad in Math 8, and you got like 30%. They would just say, okay, try harder next year, and you move on to grade 9. But once you make it to grade 10, if you fail a course, you have to redo it. There you go. There is opportunities not through our school district, but opportunities online to do courses. So you could maybe do it over the summer if you want to stay kind of current. You could probably finish a course or 2 over the course of the summer. And especially if you were kind of really close to passing and you had a pretty good grasp of things. So you could do that. You could register online, do an online course, and then be ready to start grade 11 in September. Or you could just do a couple of grade 10 courses in your grade 11 year. Nothing wrong with that either. Whatever works for you. All right, so toboggan's moving 5 forward, and it has a negative acceleration. What is the toboggan's velocity at the end of 10 seconds? So basically what we're doing here is we're going to find the change in velocity, which is going to be the acceleration times time, or yeah, let's go with that. So the acceleration in the question is negative 0.4 meters per second squared. How long did that take? That took 10 seconds. So the change in velocity is going to be negative 4 meters per second. All right, so this is where this question gets a little bit confusing because we've now found the change in velocity. We know that the velocity is changing negative 4 meters per second. So it's kind of a two-stepper. And I know that the change in velocity is going to be the final velocity minus the initial velocity. And in this question, I'm told that it starts at 5. So let's just go with this. The change in velocity is going to be negative 4. I don't know what the final velocity is going to be, not 0. I'm just going to leave it as final velocity. I don't know what it is, but I know the initial velocity it started at 5. So I'm going to subtract 5 meters per second. So if we think about some algebra, I want to get the final velocity by itself. I'm going to add 5 to both sides. And I'm going to end up with negative 4 plus 5 is going to be 1 meter per second is going to be my final velocity. So kind of a trickier question, 2 steps to it, which makes it a little bit more challenging than, say, the previous example. So we found the change in velocity was 4, and then we say, okay, if we started at 5 and we've changed by negative 4, well, we're going to be left with 1. If that makes sense. The last one's the amount of time. So we're going to go time is equal to velocity divided by the acceleration. And again, this question has a velocity that goes from 12 to 26. So my velocity is changing. I have a change in velocity. So I'm going to go final minus the initial. I'm going to go final is 26. And I'm going to subtract 12. You give me 11. So my change in velocity is going to be 11. Not 11, 14. Thank you, Josh. Sometimes when you just try to do things in your head, it doesn't work out as well as you'd hope. All right, 26 minus 12. How did I get 11? Anyways. All right, so we know that time is equal to change in velocity divided by the acceleration. We just found the change in velocity is going to be 14. The acceleration is 3.5. 14 divided by 3.5. 14 divided by 3.5. I'm thinking it's going to be around 20. If I were to guess, 14 divided by 3.5, or 4. Of course it's 4. My mental math game is weak today. 4 seconds. And the beauty of a question involving time is that we don't have to include a direction because it's not a vector. It's just, how long did it take? Well, it took 4 seconds. Does that make sense? To go from 12 to 26, you change your velocity by 3.5 each second. So I go from 12 to 15.5, from 15.5 to 19, and the next second from 19 I change by another 3.5, another 3.5, and I get to 26. Makes sense. I think. All right. These are the scenarios that we can run into when we're talking about acceleration. And the first couple make a lot of sense, and then the last few are kind of a little bit more confusing. So let's say we're stopped at a stoplight, and then we see the light turns green and we take off. So our velocity is going forward, our acceleration is going forward. in this scenario, everything's kind of positive. Everything's forward. Our acceleration's to the right, it's positive. Our velocity is to the right, it's positive. The light's green, we're moving, everything's good and happy. The problem we can run into is that our acceleration or velocity don't necessarily need to be in the same direction, which kind of makes sense when you think about it. So this is an example of that. Let's say we're driving in our car, we're going really fast and the light turns red, so we have to slow down at the stoplight. Now our velocity was forward, we were moving forward, we're cruising along, red light, slow down, we're moving forward, but our acceleration's negative. Our change of velocity is going to be negative because we're slowing down. So if we think about it in terms of a change in velocity, if we wanted our final velocity is 0 when we're stopped at a stoplight. So if we had our change of velocity as our final minus our initial. If our initial was 100 and our final was 0, if we go 0 minus 100, our change of velocity is going to be negative, and it doesn't matter how long it took, our acceleration will be negative. So I'll say that again. When you're moving forward and you're slowing down, that means your acceleration is actually negative. And remember that the negative signs with velocity and acceleration don't indicate anything other than a direction. So if you slow down, your acceleration is negative, because if it was positive, you'd be speeding up. Think about it that way. All right, a car speeding up in the backwards direction. Here's where things kind of get weird. I have a negative velocity, I'm traveling backwards, and I'm speeding up, so my acceleration is also negative. That's kind of what this scenario looks like. Everything's kind of negative. You know, you have a negative velocity to start with. Your acceleration is going to be negative because you're speeding up, going backwards. So everything's backwards. You have a backwards velocity and you have a backwards acceleration, negative acceleration. All right, the fourth scenario we can run into is kind of the hardest to kind of wrap your head around, but it shouldn't really be, but it kind of is. So let's say you're going backwards, and maybe you're like, you know, speeding up, going backwards, and you gotta eventually slow down and go forward. So if you're going backwards, your velocity is negative, but if you start slowing down going backwards, you like back out of your driveway, reverse, reverse, and then you stop, and then you can take off going forward. When you're slowing down going backwards, technically your velocity is backwards because you're moving backwards, but your acceleration is going to be positive because your change of velocity is going to be positive because your final is going to be 0 and your initial would have been negative, and then you subtract a negative, you end up with a positive. So again, change of velocity is going to be positive even though you're going backwards. So when you're going backwards, slowing down, you're going to have a sort of positive acceleration. Weird. So again, the four scenarios are this. These are the only four things that can happen. It doesn't necessarily need to be cars. It can be balls or objects or whatever. Moving forward, you're speeding up, both your velocity and your acceleration in the same direction. You're getting faster going forward. Your acceleration's positive, your direction's positive, everything's positive moving forward. Second scenario, you're moving forward but you're slowing down. It means your acceleration's actually negative. Don't think of the acceleration arrow backwards as a direction. Think of it as just being negative. Scenario number 3, you're moving backwards and you're accelerating backwards. So it just means you're going faster backwards. That's number 3. Number 4 is you're moving backwards and you slow down. So really number 4 and number 2 are the exact same, just opposite directions. So if I just had a mirror and I flipped everything, these would be the exact same, as would 1 and the fourth one, or 1 and the third one, sorry, where both things are just speeding up and the acceleration and the velocity in the same direction. All right, 3 sort of just kind of thought experiments, call them thought experiments. Can an acceleration be positive but you are slowing down? What do you think? Can your acceleration be positive but you are slowing down? We've got 2 yeses. Josh, I don't know if that's a yes or a no from before or now. I have a feeling the answers are probably written in here. Yes. All right. So your acceleration can be positive, but you're slowing down. Let's say your car is kind of looks like a truck, I guess. Your truck is moving backwards, but you're slowing down, which would really mean your acceleration is forwards or positive if your velocity was negative. So yeah, you can definitely do that. Number 2, can the acceleration be negative but you're speeding up? What sort of scenario? The answer is yes. What sort of scenario could we encounter where our car, that wasn't so good, our car is having negative acceleration but I'm speeding up? So I have negative acceleration. Which direction would my velocity have to be in order for this to increase the velocity? Probably should have wrote velocity there. So if my acceleration and my velocity are both in the same direction, I can be going negative and speeding up. In example number 3, let's assume a car's initial velocity was negative 20, just means it's going backwards. If the car has a positive acceleration of 5, what's the velocity 10 seconds later? I didn't make it far enough to erase any of this. Close your eyes. All right, so 2 different ways to think about the question. On the left, you can think about it as its velocity is changing by 5 in the forward or positive direction every second. So I should say after. So if you're going backwards at 20 and your acceleration is positive 5, after 1 second, you're going to be going backwards at 15. After 2 seconds, you're going to go backwards at 10. After 3 seconds, you're going to go backwards at 5. After 4 seconds, you're going to be not moving, so stopped. And then after 5 seconds, you're now going to start moving forward at 5. And after 6 seconds, you're going to be being forward at 10. And after 7 seconds, you're going to be forward at 15. And 8 seconds, you're going to be forward at 20. So you can see how that negative initial velocity kind of gets eaten up by the positive acceleration. So each second, you're increasing your velocity by 5 forward or positive. Let's pretend like we really were keen on using a formula to solve this question. Let's see what that looks like. So the car's initial velocity was negative 20. If the car had a positive acceleration, what would be the velocity 10 seconds later? So what we're interested in finding is we know what the acceleration is, we know what the initial velocity is, and we know a time. So if I go back up to my formulas that I had up here, my velocity is my acceleration times my time, or my change in velocity. So my change in velocity is going to be my acceleration multiplied by my time. The acceleration is 5. Just kind of forget units here for a second. That happens for 10 seconds. So my change of velocity is going to be 50 meters per second. So let's just kind of ignore the fact that we're traveling backwards at 20 to start. If I said your change of velocity is 50, you'd say, okay, let's say you started at 0 and I said your change was positive 50. So if you started at 0, you'd end at 50. Okay, let's say now you're going 10. You're going 10 meters per second forward, and I say your change of velocity is positive 50. How fast would you be going? Well, you'd end up at 60. Now let's say maybe you're traveling at 50, and I say, okay, your change in velocity is positive 50. You're going positive 50, your change is 50, so you'd be going 50, then that would increase to another 50 to 100. And we could keep doing that. We'd say, okay, you're going forward at 100 and your change of velocity is positive 50. So you were going 100, now you're changing it by 50, so now you're going to go 150. So that's how you got to kind of think about it. Now let's say, same thing, same deal. Now instead of a positive initial velocity, now let's say your initial velocity was negative. What if you're going backwards at 10? And I said, okay, you're going backwards at 10, but you're changing your velocity by positive 50. So you're going backwards to 10. If I change it by positive 50, now I'm going to be going 40. And obviously the question here has the change was 50. We calculated that, and we were initially going negative 20. So I can use a formula to describe this. Change in velocity is going to be my final velocity minus my initial velocity. So my change was 50. I don't know what my final velocity is, but my initial velocity was negative 20. And if we're going to do some algebra here, our final velocity is going to be 2 negatives gives me a positive. And then I'm going to have to subtract 20 from both sides. So 30 meters per second forward is going to be your final velocity. So even though you started out going backwards, you had an initial velocity of negative 20 because your acceleration was positive or in the forward direction, means you're going backwards, you slowed down to a stop, and then you started to go forwards again. Kind of a trickier set of circumstances. All right. Let's talk about some acceleration due to gravity, and then we'll call her a day. I know that's a lot of stuff to kind of make it through, but you got to get through it. All right, so objects near the surface of Earth fall to Earth due to the force of gravity. So we already talked about this a little bit. We talked about G-force. Gravity is a force that acts between two or more masses. So gravity isn't exclusive to planets. There is quite literally a force of gravity between my smoothie and this remote control. It's very small, but they will be attracted together. Only when objects get really, really big is the acceleration due to gravity noticeable. Like the Earth, it's pretty big. You can feel it pulling you towards it. The sun is pretty big, and it pulls Earth towards it. Earth is orbiting the sun. The only sort of human scale objects that ever experience force of gravity pulling them together happens in big super tankers in the ocean. So if you were driving your super tanker and you need to drop off some oil in a port, and you parked your super tanker next to another super tanker, because they're big enough, they actually have a force of gravity between them that's significant enough to actually physically pull them closer together. So if you didn't have any currents, you didn't have anything else, and you put two super tankers next to each other in really still water, no wind, they would actually be pulled closer together. So you and me right now, wherever you are, doesn't matter, and me, there's a force of gravity between us right now. Doesn't matter where you are, I can calculate it, but it's so small that you don't feel it. So every object that has mass exerts a force of gravity, but because something like a pen is so small, it doesn't have enough gravity for us to even notice it. But we could actually physically calculate how many newtons of force of gravity there are between me and this pen, or you and this pen. It just depends on how far you are apart from one another. So anything that has mass exerts gravity. Earth's big, so it exerts a lot of gravity. And we fall towards Earth. Right now I'm standing on the floor, on the ground, because of the force of gravity of Earth. I could try to overcome it by jumping, but it would pull me back down. And all the questions we deal with in physics ignore air resistance. I don't even think maybe second or third year university when we started to do calculations with air resistance. So just don't worry about air resistance slowing things down. Just pretend it's a perfect world. Wouldn't that be nice? All right, so if I take an object and I throw it in the air, it'll go up, it'll reach the highest point, and then it'll start to come back down. And that's pretty standard with all objects. You throw them up, they go up, then gravity says, hold on 1 second, I want you to come back, and it comes back down. So one really interesting thing about objects, when you throw them in the air, they reach their highest point. And what is going to be the velocity of an object when it reaches its highest point? At just that fraction of a second when it reaches its highest point, if I throw a pen up, the velocity was positive, because up is positive, and then it stops just for a second. Not technically a second, a fraction of a second, and then it starts to come back down. So at its highest point, an object will always have a velocity of 0, because it'll go up, it'll stop for just a fraction of a second, and then it'll start coming back down. So if we were to plot a velocity time graph of an object in free fall, it would look like this. And the numbers aren't important, but the shape of the graph is what's important. So when you release an object from your hand, it's going fast. And then it'll start to slow down. It'll go slower and slower and slower. At its highest point, it'll stop, and then it'll start to fall back towards Earth. So remember, everything in the upward direction is positive. The second that object leaves your hand, it starts to slow down. It slows, it slows, it slows. It stops at its highest point, and then it starts to go down. So it's going to have a negative velocity. So kind of a weird sort of thing to kind of wrap your head around. When you throw an object, as soon as it leaves your hand, it's not speeding up anymore. Now you've given this object a force. You've pushed it up. As soon as it leaves your hand, it's going up, but it's slowing down, and then it'll stop, and then it'll start traveling back down. And unless an object has like some sort of propellant, a propeller, or like a rocket, rockets, when they leave the ground, they're constantly speeding up. Airplanes, same sort of idea. When they leave the ground, they're usually accelerating for a while. But any object in free fall, so an object that's just thrown up in the air, as soon as it lets go, as soon as it's out of your hand, it's starting to slow down. There's nothing causing it to go faster once it's left your hand. If this object would be just happy sitting on my hand, and then I throw it, and then it goes up. But as soon as it leaves my hand, it starts to slow down. And that's what the graph ends up looking like. Suppose a rock falls from the top of a cliff. What's its change of velocity? What's the change of velocity after 1 second, or 1.5 seconds? And assume the next one is, watch this video. All right, we're gonna have to finish here pretty quick, but I think we can do this. Find the right question. Oh no, gave it all away. As it turns out, that I mentioned that objects at near the surface of Earth will accelerate towards Earth. So on Earth, the acceleration due to gravity is negative 9.8 meters per second squared. Guess we should capitalize Earth. It's kind of an important place. That's probably not exactly where I wanted to end up. So any question where an object is falling, doesn't matter what the object is, the acceleration due to gravity at the surface of Earth is negative 9.8 meters per second squared. If you were to go to Mars, seems like a pretty cool place. Some people are interested in going there. Mars has about a third of the gravity of Earth. Mars is a smaller planet than Earth. So if the gravity on Earth's about 10, If you were to go to Mars, it would only be about 3. So you could jump higher, you could throw things farther. If I threw a pen up, it would go a lot higher and come back down, just because the gravity of the planet's a lot smaller because it's a smaller rock. So let's drop a rock off a cliff. Here we go. The change in velocity of the rock after it's fallen for 1.5 seconds. So we're interested in figuring out how fast it's going after it's fallen. 1.5 seconds. Now, if you're looking at the question, you're probably thinking, there's not a lot of information here, Mr. Borden. I don't know how fast the rock started at. I don't know how high the cliff is. How am I supposed to figure out anything? Well, the good and the bad news is that all objects in free fall accelerate at negative 9.8 meters per second squared. So as soon as you see an object falling off a cliff, thrown, shot, fired, doesn't matter. If it's falling, its acceleration is negative 9.8 meters per second squared. If I fall off the top of a cliff, it doesn't say anything, but if I'm falling, my initial velocity is 0. I was standing at the top of a cliff and I fall off of it. If I'm a rock, I'm on the edge of a cliff, I fall off the edge, my initial velocity is going to be 0. It's asking to find the final velocity, so hopefully we're able to find that. And then we're given a time 1.5 seconds. So I know that the change in velocity from my formula sheet, if I go to, let's get the right page here, this is page 12, it's on the back page. Change in velocity, got this little chart at the bottom, change in velocity is the acceleration times the time. In this case, my change in velocity is going to be my acceleration, negative 9.8 meters per second squared, times a time of 1.5 seconds. It's going to be around 15, but it's going to be 14 point something. So 9.8 times 1.5, 14.7. And in this case, it's going to be negative because our acceleration is negative. So that means it doesn't matter what object. It doesn't matter how much the object weighs. It could be a car. It could be a pencil. In our perfect physics world, it's going to start at 0, and after 1.5 seconds, it's going to be traveling at negative 14.7. That's kind of, that should just blow your mind. Does that blow your mind? Mind blown. Doesn't matter what object. It could be you. I could throw you, not throw you. You could fall off a cliff. After 1.5 seconds, you'd be traveling 14.7 meters per second. It could be a car. It could be a calculator. It could be a guitar. It could be anything. After 1.5 seconds, any object in free fall will go from 0 to negative 14.7 meters per second, which is pretty interesting, I think. So the change in velocity of an object is going to be negative 14.7. All right, so let's look at a couple more examples here and then we'll finish for the day. One of the most famous stories in science is about Galileo. Galileo Galilei. That's quite a handle. It was a weird name. Lots of weird names in history. He dropped a rock off the Leaning Tower of Pisa, and what he did was he dropped 2 different objects. So he had a big rock, a little rock. He took them to the top of the tower, and because the tower is leaning, you can drop stuff off it. It's not going to hit anything on the way down. A big rock, small rock, both fell at the same rate, just like we were just implying in the last question. If you were to fall next to an object like a car, you guys would both fall at the same rate. And it turns out that this is true for any object that you drop. You run into problems with air resistance, though, and we'll look at that a little bit maybe next day. So again, it doesn't matter how much an object weighs. You could drop 5 kilogram mass and a 2 gram mass, like a penny or something, and they will fall at the same rate. Now, one really cool thing that happens as a result of this is that if you go somewhere without air resistance, like, I don't know, say the moon, there it is, objects will fall at the same rate. And this was actually an experiment that, I forget the guy's name, and I forget the Apollo mission. I think it was maybe Apollo 11. They went to the moon, and they dropped some objects on the moon. And the moon doesn't have an atmosphere, it has no air. So he took a hammer and a feather to the moon, and he dropped them. And the quality is not great because it was from the 1969 or 70 or 70 something. But you can see that these objects are going to fall at the same rate. So here he is. Right hand's a hammer. Oh, this is really slow frame rate. That's okay. So he's got them, and he's going to drop them. And they should hit the ground at the same time. He's kind of going on about how Galileo, did this experiment, famous experiment, Leaning Tower of Pisa, dropped some objects, and here we go. You can kind of barely see it, I guess. The quality's not great, but the objects did, in fact, hit the ground at the same time. We can do the same experiment in a vacuum chamber on Earth, and maybe watch this video next day, just because I don't want to play it now. It's a few minutes long. Let's see exactly, 4 minutes. So NASA has a big vacuum chamber, and they repeated this exact experiment in the vacuum chamber, and it's quite interesting to watch. So, Mr. Ross, you need to leave in 15, is that right? Okay. Let's do a few more examples here, just 3 more, and then I'll let you guys go. So the questions you're going to deal with in this part of the course are exactly the same as the ones we would have dealt with before, but with the added bonus that you know the acceleration of any object that's falling near the surface of Earth, which is kind of a nice bonus. Wouldn't you agree? You should agree. All right, so let's do these 3, and then I will sign off for the day. So if you consider up to be positive, what does the acceleration due to gravity on a dropped stone? Any object in free fall is going to have an acceleration of negative 9.8 meters per second squared. And I will mention that you do need to memorize that number. That's probably the only, well, not the only, but one of the only numbers that's like super duper important to Science 10 that you'll have to actually know. It's not on the formula sheet. I don't know why. It should be. It's not. So if you throw a rock up into the air, when is its velocity 0? And what is the acceleration when the velocity is 0? So if you can answer this correctly, you're brilliant. So let's throw an object up in the air. It goes whoop, and it gets to its highest point, and then it starts to come back down. We know, we've already discussed that its velocity will be 0 at its highest point. But what is the acceleration? So what is the acceleration at its highest point? What do you think? Anybody want to take a stab at that one? A guess? Shot in the dark? Object's highest point. What's the acceleration going to be? Any object that's in free fall should have the same acceleration. It should be negative 9.8 meters per second. But at its highest point, it stops moving. Does this acceleration change? When I throw an object into the air, before you answer, Eric, I don't want to put you on the spot, but if I throw an object into the air, it goes up, 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 it stops, and then it comes back down. Does the Earth, big ball of rock we're currently residing on, does the Earth know when an object's thrown into the air? Does it know to shut gravity off when an object gets to its highest point? Just think about that for a second. Does it know if I had to jump into the air, Did gravity know when I got to the highest point to say, okay, he's at its highest point. We should shut gravity off for a second. Stop gravity. No more gravity. Jeremy's at his highest point. And then gravity just disappears. Is the acceleration due to gravity 0 when everything gets to its highest point? Or does any object in free fall, regardless if it's moving, not moving, experience the exact same acceleration due to gravity? What do you think? It's always negative 9.8. So even at its highest point, an object will have an acceleration of negative 9.8 meters per second squared. Doesn't matter if an object's just starting its way up, if it's falling, if it's been dropped out of an airplane and it's been falling for 5 minutes, if it's at its highest point and it stops, doesn't matter. If an object is in free fall, meaning it's not being propelled by anything, it's just falling, doesn't matter if it's going up or down or stopped on its way up, the acceleration will be the same. So we'll do this last little guy here. Stone is dropped from a cliff. What is the velocity after 1 second? Again, it doesn't say anything about the mass of the object. Doesn't matter how big it is or small it is. Doesn't matter how much it weighs. All objects are the same. So here's my rock. At 0 seconds, it's traveling at 0 meters per second, and my acceleration is going to be negative 9.8 meters per second squared. All right, let's go 1 second later. My object should travel a little bit. How fast will it be going after 1 second? If every second the object's velocity changes, its acceleration is negative 9.8. After 1 second, how fast should it be going? If every second it changes its velocity by 9.8. 1 second later, object should be going negative 9.8 meters per second. And its acceleration will be negative 9.8 meters per second squared. All right, let's go a little bit further here. Object is going to go another second. All right, so we're at 2 seconds. What's my velocity going to be now? Doesn't matter what the object is. Rock, you, me, my smoothie, 9.8 meters per second every second. It was going 9.8. It should be going 19.6. How'd you get that number, Eric? Because it's right. Acceleration, still negative 9.8 meters per second squared. You doubled it. Brilliant. I like how you think. Another second. I know it says to go to 2. We're gonna go for broke here. After 3 seconds, how fast will an object, a rock, you, me, anything be going 3 seconds after it's fallen in our perfect world? 9.8. Eric, you doubled it. I'm going to triple it this time. 29.4. So it'll be going negative 29.4 meters per second. Acceleration, still negative 9.8 meters per second squared. 4 seconds later, I'm going to go 9.8 times 4. I'm up to negative 39.2 meters per second. Acceleration, still negative 9.8 meters per second squared. So objects in free fall will change their speed by 9.8 meters per second every second. And that change will always be down or negative because objects are going to speed up or slow down depending on their initial velocity. So there you go. That's acceleration. This is kind of the meat and potatoes of the physics unit. This is as difficult as this unit gets. And when I do this unit, I usually get to this point and students are kind of like either they really just get it or you really don't get it. And it's going to take some practice. So don't just think, oh, I don't get it, I'm just going to give up. Well, try some of these questions. I mean, a lot of the questions are going to be really straightforward. There's going to be some trickier type questions that have some calculations involved. Use a calculator, use the formulas. The most difficult thing I would say is being able to identify what the question is telling you and what the question's asking you. So there's one section left in the course which we'll do on Tuesday. The learning guide has just a absolute smorgasbord of questions on this type of stuff. Some of them are easy, some are hard. Most of them are easy. But there are 17, 18, 18 questions for you to go through. And it's just kind of a challenge with the course. The learning guide answer key, unfortunately on question 17, some of the answers are wrong. So careful. Don't just copy the answers out. I'll know you copied them. Some of them are wrong. So be careful on 17. Everything else is worth a shot. Try them. See what you can do. Think about it. Use your brain. You might be surprised. There's a lot of sort of theory questions and not necessarily all sort of calculation type questions. So there you go. For next day, what should you do? You should do section 9.1 out of the learning guide. We're going to have class on Tuesday. We will finish up section 9.1. I'll answer any questions you guys have. But please try the questions. I am really good at the questions. I've done these questions many times. You, as a whole, all of you, would benefit from trying them yourself. See where you run into problems. But don't come to class next day and just be like, I didn't do it. You got to try it, because there's no way to be really good at this stuff or to know how to do without trying it. So you need to actually try it. So do that. You should hopefully be done Unit 8, and that test should be probably done today or tomorrow. That would be spectacular. That's kind of it. We'll have our last class of new material next day. We'll finish up 9.2, which is just a graphing section, super quick, super easy. And then we can start review on Thursday, and then again on the following week if necessary. So that's kind of where we're at, where we're going. I hope you guys try this stuff. Come back with questions the next day. I'll be happy to go through them with you, but only if you try them. And I'm going to sign off for now. So I hope you guys have a great weekend. We will see you guys in class on Tuesday, and try these questions, please. Thanks.